Hello AP Chemistry and welcome to the back part of 16.9, the section on salt solutions. So, just a couple of special examples, right? Your book mentions amphiprotic species, right, where amphiprotic, right, means they can either give a proton or accept a proton, right, and your book gives you this example, I think, right, where it could, right, become H2SO3, right, or it could become SO3 2-, right? And how it's going to behave, right, is going to depend on its Ka versus its Kb value in terms of what it's going to do with water, right? And so that's a special example in that we would need to know those values, right, to know what HSO3- is going to do in solution, right? This goes back to that Fe example we were talking about on the previous video, right, where this is relatively acidic, right, based on that K value, right, for small, highly charged cations, right? And note we're talking about 2 or 3 plus, right? And they're all relatively small, right? If we think about our periodic table and where these elements fall in terms of periods, okay? And what it really means, and we don't get into complex ions in the scope of AP Chem, but like if you look at your book, what happens is that iron, right, being a cation, right, gets surrounded by those water molecules, right, again, in a direction-oriented manner, right, because here, if we look closely, right, we'll see that these are those oxygen ends, right, preferentially attached to that iron, right, but they're attached in such a way, right, that they actually form their own species called a complex ion, right? Because waters are neutral, there are 6 waters, but the overall charge of this complex ion is still 3 plus to reflect the charge of the iron since the waters are neutral, right? But what happens is that when that positive iron interacts with these negative oxygens, right, or the partial negative oxygens, electron density is pulled away from the hydrogen. Yes, electron density is pulled away from the hydrogen. And as electron density is pulled away from this hydrogen, it is more easily abstracted, right, by the lone pairs on a neighboring water molecule, right? Which means that we then form this ion, right, and that ion in solution, yeah? So that's always something to look out for. All right, so some quick practice here. So which is the more acidic or less basic of each of these solutions, right? Okay, so then remembering, we're going to go back and ponder the implications of the cation versus the anion, right? So our anions are the conjugate bases of some acid, right? And these are going to be the conjugate acids of some base. So we just need to go back one step and decide whether or not that acid was strong or that base was strong, which will then tell us if that ion, right, has a tendency to be acidic or basic. So if we come over here and we're looking at sodium nitrate, right? Sodium, right, thinking about the base that it came from sodium hydroxide, right? Negligible, because that's a strong base. Nitrate comes from, right, nitric acid, right, which is a strong acid, so negligible basicity, right? Then if we look at the FeNO3, right, which means that this one would be neutral, is the point, right? If we look here, nitrate, same reason, right? Iron, small, highly charged cation, which means that this solution would be acidic, right? So the more acidic solution would be iron nitrate, right? Moving along, here we have KBr, same thing, right? K comes from potassium hydroxide, irrelevant. Br comes from HBr, irrelevant, so this would be neutral, right? K, same thing, irrelevant, but this, the hypobromite ion comes from hypobromous acid, which is a weak acid, which means that this has a tendency to be basic. So the more acidic one is actually going to be KBr, yes? All right, next up, we've got some this and some that. So let's do this one first. This one's easy. Barium comes from barium hydroxide, which is a strong base. Chloride HCl, right? So then that leaves us with this. We have a nitrogen stuck to 1, 2, 3 things, right? This is a cation, right? This is that amine that we talked about, right? Which means that this is correct, acidic, right? And this one is neutral. So then if we were picking, right, the most acidic one would be this one. All right, last up, we have ammonium. So ammonium, again, is the conjugate of ammonia, which means that this is acidic, right? Acidic. Now, nitrate comes from a strong acid, which means negligible basicity, right? Nitrite comes from a, right, weak acid, which means that this is basic. So if we're looking at the question, and the question is just asking us which compound is overall more acidic, it's going to be this one. Yes, does that make sense? In that there is nothing to mitigate the acidity of the ammonium, right? Whereas in ammonium nitrite, right, the nitrite's basicity mitigates the acidity of the ammonium. Yes, does that make sense? All right. Okay, so then analyzing the next one. So we're going to predict whether the dipotassium salt of citric acid is acidic or basic, right? So here, again, we'll cross that one out because we already know that one, right? So that leaves us with that, right? So we have this Ch16H5O7, right? Which, since there's 2 potassiums, mean this is 2 minus, right? But we'll see here, right? So we had 3 acidic protons to begin, right? We have 1 acidic proton, which means that this is, right, one of those amphiprotic species, which means that there is a possibility it could do this, right? And it could end up taking a proton from water and doing that, right? In which case this is a what? This is a KB process, right? Or there is also the possibility that it could do this. Which is a Ka process, right? So we're looking at the Kb value of this, right? And if we go over here, that's going to be the inverse, well, not the inverse, but that's going to be Kw over that, right? Does that make sense? Kw over that. This is just going to be the Ka value of that, right? So the Ka value for this is 1.7 times 10 to the negative 5. The Kb value of this is going to be something in the range of 10 to the negative 9-ish, right? Something like that. Which means that this is more likely to behave as an acid than it is to behave as a base. Yes, it is more likely to behave as an acid than it is to behave like a base, right? Given that the Ka value of it is larger than its Kb value, which means that the solution formed would be acidic, since potassium does not add any mitigating factors to that. Yes, does that make sense? All right, thank you for listening. Be good. Make sure all this makes sense.